welcome back to another video in this series. So EIGRP, and this one is metric calculations. So we'll be exploring how it goes about creating the values that you'll see in your routing table and the topology tables. There are multiple items that it uses for its metric calculation. Now, these can be adjusted throughout your topology. You get to decide which elements it's going to use, but the default elements it uses is bandwidth and delay. We can use load and reliability of the interfaces. Now, the only issues with these is it's not dynamic. It is statically assigned by us as the administrator. So it's not really a true reference of the load or the reliability of the link. It's our interpretation of those values for use. So, what determines what elements we use? Well, they're called K values. And these are set to either 1 or 0 to enable that element to be used or not. So if you look at the classical formula, we have K1 by bandwidth plus K2 by the bandwidth divided by 256 minus the load plus K3 times delay. All of that gives us one value, and then we times that by K5 over K4 plus reliability. Now, what's that all mean? Well, our calculations have to take into effect which elements we are using, and basic maths, if a value is 0, so a K value is 0, it cancels out the multiplication. So when we look at the bandwidth, we're looking at the slowest link in the path, and it's scaled up to 10 gigabits per second, which is 107. So we're looking at the bandwidth as configured on interfaces. Now, in today's age where everybody's using Ethernet, it's not, it's in scales of 10 from each other. It's pretty easy to see what's going on. But if you're an old person like myself, we're around with serial interfaces with leased lines. We had a great variation in WAN links. So this created some interesting dilemmas for us, because we had to go through and make sure we adjusted the bandwidth on each interface to properly represent the bandwidth available through those interfaces. The delays are cumulative throughout the path and are measured in tens of microseconds. Now, with the advent of time, we went from interior gateway routing protocol, which was the original formula, and this used 24 bits to come up with a value. Cisco decided when they brought out the enhanced version, they would times that by 256, just so that it had 32 bits variation and gave some backward compatibility between IGRP and EIGRP. So when we look at the K values, and remember that we've only got K1 and K3 set to 1, all the others are set to 0, we can look at the impact on the metric, and it comes down to 256 times 10 to the 7 divided by the minimum bandwidth plus the total delay divided by 10. So this is our default metric here. Is there any reason to go and change any of the K values? Not really, but you can if you want. Just be aware that when you change one of these values on one device, you need to go through and change it on all your devices, because the metrics, the K values, all have to match for your neighbor relationships to form. So if you change it on one device, it's not going to form relationships with other devices. So how does this work when we see it going up through a path? So as EIGRP travels through your network, the attributes are attached, such as hop count, the delay is added up, and the minimum link speed or bandwidth is included in each update. So as the update from router 1 for this network comes out, it's hop count 0 because it's directly connected. Link speed's 100 megabits, delay's 100. So we get a reported distance. Then as it arrives at router 2, adds 1 to the hop count because it's got to go via another device. Its minimum bandwidth is there, total delay is added up, and we get a new reported distance. Then off it goes to router 3, and we have the minimum bandwidth still at 10 because that's the slowest link in the path. It's totaled all the delays together, and it's now got a feasible distance because this is the calculation point of how to get to this network from this device. So here we can see how the bandwidth and delay greatly affected the metric calculations. So the slower the link, generally speaking, the higher the metric value. So you can see here there was quite a variation in delay, but these lose a little bit of differentiation depending on the technology of the interface. And remember, these are also the default values of the delay based on the interface type. So how can you know which ones have an impact on the metric? Well, if you use the command show IP EIGRP topology, you'll be able to see what parameters are in effect for the metric. Now, with the advent of the named configuration mode, we have a change. We now have a K6 value. So this is known as wide metrics, and the formula has changed a little bit. So we now have this K6 by extended value here inserted in. Now, the issue we have with this is it's changed the metric. So we have an issue with classic mode and name mode because the K values won't match. So we're not going to have the same metric calculations throughout the entire network if you got them both mixed together. So what do? Well, we want the name version because of its ability to scale to a much wider, broader selection set over newer networks. So what we need to do is to make the move from classic to named across our networks. Why do we need to do this? Because it provides our support up to 655 terabits per second. So it's much more scalable and gives us the modern differentiation between the bandwidths we see in networks today. So when we come back and look at how this interacts with our network, classic configuration, they can't really coexist within the same network. There is backward compatibility, okay, but we will lose the correct metric that should be in use on Y-metric enabled devices. Because of the backward compatibility, they default back and don't use the K6. So that's this slide. So it becomes a bit of a problem because we lose that clarity of the path throughout. So rule of thumb, don't mix your configuration modes throughout the network. If you're modernizing your network and using the higher speed links, then I would recommend you plan to convert from classic mode to name mode so that you get a better clarity on your pathing throughout your modern network. Now, as I mentioned earlier, your metrics are all based on your interface settings. So your bandwidth, your delay, your load reliability are all on a per interface basis. So if we're using our standard two values, our bandwidth and delay, these are the things we can change to affect our calculations easily throughout the path. So if you go into your interface, type in delay and then give it its new value, remember these are in tens. Okay, so 100 equals 1,000. So we can change our delay to give us a different metric calculation. So we can change and impact our path to determination by just making a simple adjustment in a delay on one interface, and that will change our preferred pathing throughout the network. Now, metric weights is the command that you want to enter for the changing of the metric calculation. But you don't just go in and change it on one value. You actually have to put in all k values. So you always have a series of ones and zeros after the metric weights. So if you're using classic mode, you need to have 5 values. If you're using name mode, you need 6 values to represent the different k selections. Now remember, all your devices within your autonomous system need to have the same k values for it to form adjacency and exchange routing information. K values are sent within the hello packets if you cast your mind back to the other videos. To check, show IP protocols will display what the k values are. Now, EIGRP allows for 4 equal cost load balancing by default. We can change that if we want by using maximum paths, and we can change the number of paths that it will load balance over. So you'll see there the 2 modes. So if you have a look, it's very easy on the classic. Just go in the router EIGRP, maximum paths, and the new value. With our extended one, our named, we need to go into topology base and then adjust it there. EIGRP also allows us to have unequal cost load balancing. We do this by changing the variance multiplier that exists. So by default, the variance is 1, which means equal cost. If we change the variance to 2, then that changes the number of feasible successes that can be included. So the feasible distance for a route is multiplied by the variation, and any feasible successes that are then enabled are included into the topology for load balancing. So it's a good way of making use of bandwidth. And you go, what? Well, the faster bandwidths would have a higher proportion of the traffic than the slower ones. For example, you might go 3 packets sent down the primary, and then 1 sent down the secondary. So it load balances across these variable paths in ratios that are equivalent to the bandwidths that are available. Why does it do this? So that they basically should arrive in order at the other end. It's quite a nifty little feature. Okay, that concludes our basic fundamentals of EIGRP. Chapter 3 will go through more advanced features of the protocol. But the next video in sequence will be a lab, so we actually do the configuration items in Packet Tracer. So, thanks for watching, and I'll catch you in the next video. Bye for now.